short review. Remember, delta G, the change in the Gibbs free energy for a reaction, determines the spontaneity of that reaction. So what is the condition that must be satisfied? Delta G reaction is less than 0 under what conditions? Constant temperature and pressure, and most chemical reactions, 99.99% of chemical reactions are conducted under constant temperature and pressure conditions. So the second law of thermodynamics becomes delta G reaction is less than 0. This equation applies to all conditions. This applies only to reactions that are being conducted under constant temperature, constant pressure conditions. And we saw that delta G reaction is equal to delta G reaction natural log of Q. What is Q?
Partial pressure ratio.
Okay, it's a ratio, but what is the name, the technical name for Q?
Quotient.
The reaction quotient. Okay, Q is the reaction quotient. And Q is equal to, so if we have a reaction A plus B going to C plus D, Q is equal to, what is Q equal to? P, C, P, D over PA. Okay, that's the reaction quotient. Okay, and at equilibrium, what's the condition? At equilibrium, the condition is? Marina?
It's a constant, right? That when Q becomes K, that's
Q becomes K, but how does Q become K?
Under equilibrium.
Under equilibrium condition, what happens?
it equals 0.
What equals 0? Delta G reaction is equal to 0. And if that is true, what does this equation become? Delta G naught reaction becomes equal to minus RT natural log of K. And K, what is K? So the reaction quotient at equilibrium, and therefore that's equal to the partial pressure of C to the power C, partial pressure of D to the power D, over partial pressure of A to the power A, partial pressure of B to the power B, all evaluated at equilibrium. We can also write this equation as K is equal to e to the power negative delta G naught reaction over RT. So what is delta G naught reaction?
Delta E negative delta H.
No, I'm asking you to define what is delta G naught.
The reaction at standard temperature and pressure.
Okay, when we talk about standard conditions, we don't specify the temperature. We say usually 25 degrees centigrade. Okay? So, delta G naught reaction is the change in the Gibbs free energy when reactants in their standard states go to products in their standard state. Okay, that's what delta G naught reaction is. That quantity depends only on delta G naught depends only on what? Temperature. Delta G naught reaction does not depend on pressure. It doesn't matter whether you conduct the reaction at 1 bar or 10 bar or 100 bar. Delta G naught reaction is a constant for a given reaction at a given temperature. Very, very important. And therefore, the equilibrium constant K is a constant for a given reaction at a given temperature. A very, very powerful observation. In fact, chemistry 205 is all about equilibrium constant. The application of equilibrium constants to problems in environmental chemistry as well as issues related with blood pH. Equilibrium constant plays an important role in organic chemistry also. Okay? So, I'm going to finish up yesterday's lecture. I hope every one of you picked up one of these handouts, both of these handouts. It turns out I have only one more lecture before we finish the material for the next midterm. I know. One more lecture before I finish the material for the next midterm. So I'm now one lecture behind, but that's okay. I want to make sure that everybody understands what we're doing. So that's why I'm going to spend most of my time today reviewing the material. Okay. Any questions on the logistics? Okay, yes?
What is the next one?
That I do not know.
26.
Okay, 26th. And unfortunately, Chem 105 will be coming to an end. Okay, all right, let's get back to lecture number 21. This is the outline. So here is our favorite reaction. This equilibrium constant, the way I have written it in terms of partial pressures. So I have to put a subscript here to indicate that this is an equilibrium constant expressed in terms of partial pressures. Equilibrium constants can also be written in terms of concentrations, in which case it will be the concentration of C to the power C, concentration of D to the power D, divided by the concentration of A to the power A, concentration of B to the power B. We will talk about the relationship between K sub P and K sub C in the next lecture. They are related, but they're not the same. So here are some examples of equilibrium constants. H2 plus O2 goes to water. What can you tell me about this reaction? By looking at this table, what can you tell me about this reaction? It is extremely product favored. Okay, the equilibrium constant is 1 times 10 to the power 83. In class yesterday we found the equilibrium constant for the reverse reaction, and we found that it was 10 to the power minus 84 or something like that. So whenever you specify the equilibrium constant, you have to also specify the temperature, because the equilibrium constant depends on temperature. And you can see the temperature dependence. Remember, we plotted a graph to show the temperature dependence of the equilibrium constant. What did we plot on the y-axis? We plotted log of k and inverse t. And the slope of this line was negative delta H over R. So in the case of an exothermic reaction, delta H would be negative, therefore the slope would be positive. And if you increase the temperature, the equilibrium constant becomes, if you increase the temperature, the equilibrium constant becomes smaller, because if you're increasing the temperature, you're going in this direction here. All right? So the magnitude of the equilibrium constant tells us if an equilibrium reaction is reactant favored or product favored. If K is much greater than 1, the reaction is product favored. If K is much less than 1, the reaction is reactant favored. So let's look at a reaction.
Nitrogen monoxide does not react with water. When it contacts oxygen in the air, however, the reaction is almost instantaneous and produces the brown gas, nitrogen dioxide. The reaction is so product-favored that a chemist would say that it has gone to completion, a fact reflected by its very large equilibrium constant.
Okay. So this is a large value here. So how would you write the K sub P for this reaction? What's going to be in the numerator? The partial pressure of NO2 squared divided by the partial pressure of nitrogen monoxide squared multiplied by the partial pressure of oxygen. You should be able to write the equilibrium constant expression for any reaction. Let's look at a reactant favored reaction.
When we mix a solution of lead nitrate with a solution of potassium iodide, a precipitation reaction produces lead iodide. Lead iodide is only slightly soluble in aqueous solution, so its dissolution has a very small equilibrium constant, and the reaction is considered to be reactant favored.
So here is the reaction corresponding to dissolving lead iodide. It has a very small equilibrium constant. If we write K sub C for this reaction, what will be in the numerator? concentration of lead 2 plus multiplied the concentration of iodide squared. But in this case, we do not put the concentration of lead iodide in the denominator. Whenever you have a pure solid or a pure liquid, we will see in class on Wednesday, another 6-day vacation from chemistry. Okay? The denominator does not contain this quantity here. We will prove that next class.
So what is the equilibrium constant?
The equilibrium constant is just going to be lead 2 plus the concentration multiplied by the iodide concentration squared. Yes.
And why is it that you're comparing the concentration?
So here I'm using K sub C.
Yeah. In what situation would you use?
You wouldn't use K sub P here because there's no partial pressures. These are not gases.
Okay.
When you're not having gases, you have to use K sub C. But if you have gases, then you have the choice between K sub P or K sub C. Neha.
When you're writing it, is it just iodide or do you put the 2 as well?
No. Okay, let me write that out. So when I write this, K sub C here would be lead 2 plus times I minus squared. So what can you, yes, Chrissy?
So, could you explain one more time when you use the equilibrium constant versus the reaction coefficient?
Reaction quotient. So, when you're given a quantity, here you're given the equilibrium constant.
Okay.
So then all you're doing is writing out these at equilibrium. You use the reaction quotient when the system is not at equilibrium.
Oh, okay. So is that why you don't need the denominator? Or?
No. That denominator, that has something to do with the fact that this is a pure solid. Remember, okay, if you go in the previous example, in the denominator you had NO and O2. Okay? This is a special property of the fact that when you have reactants or products that are pure solids or pure liquids, they do not show up in the equilibrium constant expression. I will give you a proof of that in the next class.
Okay.
Yes, Marina.
What if a reaction is like has gases, liquids, and solids?
Very, very good. In that case, you will learn in Chem 205 that the better method to approach these problems is to use a concept called activity. Okay? We will deal with that in a very superficial manner, but we'll talk about that in the next class. Okay? But really, all of this K sub P, K sub C will all disappear in Chem 205 when you talk in terms of activity. Okay? But to understand activity, you really first have to understand K sub P and K sub C. Look at very simple examples, and you will see that a lot of what I'm telling you is not quite true. Okay? Things are a little bit more complicated. That what we're talking about is the ideal situation. We're talking about ideal gases. Real gases don't. It turns out that K sub P actually depends on pressure. Okay? No. You didn't hear that, okay? Just completely ignore what I just said now, okay? Until you finish Chem 105 and start Chem 205, we will keep everything very simple, all right? Chrissy, did I answer your question?
Yeah.
Okay. So let's look at what happens if we take the equilibrium constant of a reaction and compare it to the inverse of the reaction. So here, is one reaction. Here is the inverse of that reaction. What is the relationship between the equilibrium constant? They're inverse of each other. Okay, does that make sense? Write the equilibrium constant expression for this. Write the equilibrium constant expression for this. They're going to be inverse of each other. So these values are going to be 1 over the other value. So let's look at this equation here. Here is the process for dissolving lead iodide in water. The equilibrium constant is this. We take this same equation and we multiply it throughout by a factor of 2. If we do that, the new equilibrium constant is going to be the square of the previous equilibrium constant. So if we multiply any equation by a constant, the new equilibrium constant is going to be the old equilibrium constant raised to the power of that constant. Does that make sense? So we multiplied by a factor of 2 here, therefore Kc prime is going to be K sub c squared. If you multiply by a factor n, K new is going to be K old to the power of n. So whenever you write an equilibrium constant, not only should you specify the temperature, but you should also have an accompanying equation written for that process. So, supposing we know the partial pressures of the reactants and products at equilibrium, we can plug into this equation and get K sub P. If it was K sub C, it would be the concentration of C to the power C, the concentration of D to the power D, concentration of A to the power A, concentration of B to the power B. All right? Using that, can you set up the problem here and solve this problem, please? Has everybody turned in their quizzes?
No.
Thank you. And the answer is and the answer is 4.08 times 10 to the power 8. Questions? Yes.
When you say, because there was a 2 in front of the energy, is that what you raise it?
Right.
Okay.
Yeah. So
Okay, that
look,
makes sense.
A, B, C, D, they all go in the exponent.
Oh, okay.
Yes, Rachel.
So whenever you calculate K sub C, should you always just consider it to be in molarity?
Yes. Yes. And you also note the fact that really you are dividing all the concentrations by 1 mole per liter. So the numerator and the denominator do not have units, and your final answer does not have units. So basically what I'm saying is that P sub C has to be divided by 1 bar, P sub D has to be divided by 1 bar, and similarly C has to be divided by 1 mole per liter, D has to be divided by 1 mole per liter, and so on and so on. So none of these terms has units. So the final answer has no units. Questions? Yes, Erica.
I still don't really understand why you divided by 2.
Oh, so C is the concentration. Concentration is molarity. Molarity is moles per liter. So you have to take the number of moles and divide that by the volume. What's here is concentration. It's not the moles of C raised to the power C. It's the concentration of C raised to the power C. Questions? All right, let's spend the rest of today's class working on those multiple choice questions. First do MCQ.